There are many ways, of course, but you could just 1, 1/2, 1/2, 1/4, 1/4, and so on, and it's oriented like this. Then you see that the incoming flow is the same as the outcoming flow. And so this thing, it's not an L1 cochain, as you see, but it's an L2 cochain. So it's square summable. It's not summable, of course, it means certainly not, but it's square summable. And there are many ways. It's an infinite dimensional space, the H1. So this labeling of the edges, I described your one cochain that is in the kernel of the star, and as we've seen, this gives you then a non-trivial element in H1. So, so the 3T here.
Just coming out of, because you need half and half on the left side also.
On the left.
Yeah, it goes
do
on.
the same.
Do the same. You mirror it somehow.
But then if you square all the halves and sum it up, you get.
I mean, if you sum it up here and it's smaller than infinity, then also the sum here is smaller than infinity, and the whole thing will be smaller than infinity.
See, half square is 1/4, and when you sum it, it's 1.
Now, when you start, you have 2 times 1/2 over 2 plus, then you have 4 times 4.
I looked on the first step and not the.
This is summable. It's, as I said, it's not summable, it's square summable.
This one is summable.
Yes. No, I guess the L1, I'm not sure. I guess the L1 homology should be 0, actually. There should be no L1 cochains. Alright.
So is it easy to see the dimension?
Well, we only seen this, and we don't have the dimension yet. I haven't defined it yet.
Okay. You see that you have infinite choices for your parameters.
Yes. Yes. Okay. So now, before I come to the dimension, which will be the next major part, I want to comment on 2 viewpoints of this L2 cohomology in the case that you have a group action. As I said, or it was kind of a promise that we will define the L2 Betti numbers as some sort of dimension of the L2 cohomology of a gamma space, namely universal cover. And I said that the dimension will take the gamma action into account, but then I left the gamma actions and just explained what is the L2 cohomology of CW complexes. And but now I want to come back to this situation where this spaces I look at arise as universal covers of actually complex CW spaces. So they have a nice co-compact group actions by deck transformations. And then, especially in the case where this universal cover is a model of E gamma, classifying space of the group, this L2 cohomology can be written in a different way, in a more algebraic way. Okay, so this is a just think 1 second. All right. So this is a remark. That if the space Y that I considered in the general definition of the L2 cohomology is E gamma, then this L2 cohomology, let me first write it without this bar, so not taking the closure of the image, just the usual thing, is isomorphic the group cohomology with L2 gamma coefficient. Well, that's true. And the gamma is compact, I should say, or finitely number complex. There is some technical thing here. But, okay, so this is for those of you who know that there is such a thing as usual group cohomology of a group. And this group cohomology has coefficients, so you can put any gamma module as coefficients, and there's this gadget. And it turns out that in this case that you have y is B gamma, so the universal cover of B gamma of a group gamma, and B gamma happens to be compact, then this L2 cohomology is, without the bar, is just this. So it's a very algebraic object. And I can give you the isomorphism. Just thinking which direction was the easier one. So this is an exercise. In this direction is maybe easier to write down. And well, to write down this isomorphism, you need a nice model for this thing here. So the thing is that you can compute the group cohomology using E gamma. So this just assumes now some knowledge that, I don't know, some might have, some don't. But this is just a remark. So you can compute this group cohomology using E gamma in the following way. Take gamma equivariant maps on the chain complex of E gamma on which gamma x to L2 gamma. And L2 gamma the regular representation of the usual gamma action. And remember, this was just hi of this. So now I have to give you a map from the right to the left, and I give it to you on the level of chain complexes. So if I have an equivariant map from C gamma to L2 gamma, I have to map it to an L2 map on the set of, say, I cells, and this is the map. So E is an I cell in E gamma. It is mapped to the coefficient of E of F E. So here I need a map from the set of I cells to the reals that is square summable. What I start on this side is an equivariant map from the I cells to L2 gamma. So I take my I cell here and I look at this Fe. Fe is an element in L2 gamma, and I look at the coefficient of the unit element. This is just a number. This is the number associated.
Yeah, but now we're using E in two different.
Oh. Thanks. Yeah.
You're also using eyes.
No, wait, one of them is the cell E.
This is the I cell E, and I map it to the coefficient of the unit element. And I view the unit element as the element of gamma, and gamma is a subset of L2 gamma. And here I did another mistake that I correct now, which is this. Okay, so now there are things to check. I mean, it's actually an isomorphism on the chain level, and in particular it gives you an isomorphism. But somehow you don't have to do it now in your head why this is an isomorphism. Just wanted to give it a map somehow. But my point is just to say that this object here in this special situation is actually something very algebraic. It's a group cohomology group. And okay, if I take the bar, it's something smaller, but still it has a very algebraic meaning. And these two descriptions, this description has L2 cohomology that somehow does not use the gamma action at all. And this description, that's very much group theoretic. To have both is a very useful thing, and it's a good tension to have, this group action picture and this purely geometric action picture. For example, these things are used in a theorem of Ponceau that I just want to mention at this point, and it says that the vanishing of the ith Betti number of a group is a quasi-isometry invariant. Okay, so if you have a finitely generated group, you can put a metric on the group called the word metric, and then you call two such groups with chosen word metrics quasi-isometric if they are bi-Lipschitz as metric spaces. Bi-Lipschitz not meaning that there is a bijection, meaning just you have a map. Bi-Lipschitz equivalent. Lipschitz map in both directions, and the composition is close bound distance from the identity. So there are somehow the coarse geometry is the same, and this theorem is a very nice thing, and it's not so hard to prove with this picture, because the vanishing of the ith L2 Betti number, whatever it is, I already told you, is just the vanishing of, well, of this reduced thing. Now, as I said, if you have now two groups that are quasi-isometric, let's call it gamma and lambda. Actually, for this theorem, you also need that you have models of E gamma and B lambda that are somehow nice, so that the B gamma and B lambda are compact. You actually don't need it in the end, but somehow for the idea that I give you need it. But let's not worry about details. So, if you have these two models and gamma and lambda are quasi-isometric, you can show that there is also a bi-Lipschitz map between E gamma and lambda. And so somehow the metric, this guy as a metric space, somehow you put on every simplex the usual Euclidean metric, you get an induced path metric, so this comes with a metric. And these metrics on E gamma and E lambda are also coarsely, in a coarse sense, equivalent if gamma and lambda have somehow the same coarse large-scale geometry. And then you have to see, and it's not very hard, that this thing here, as I said, it's not functorial with continuous maps, but it is functorial with respect to bi-Lipschitz maps. It's not hard to see. And if you have this bi-Lipschitz equivalence, you see that it induces isomorphisms on this level, and therefore vanishing of the L2 Betti number, which is vanishing of this group, is a QI invariant. So it's a short outline. I mean, there are many details to fill in, but actually also not too many, so it's not really hard. But it's a very useful thing to have this description, because if you look at this description, you have two QI groups. There's no algebraic map a priori that you can use between gamma and lambda that gives you something in group cohomology, because it's just a metric notion, this quasi-isometry. But on this picture, somehow the group action is gone, and you can compare two things. So it's good to have both points of view, although from now on I will stress a little bit more the algebraics. Okay, so let's get finally to the definition of L2 Betti numbers. So let's get finally to explaining what is this dimension that I talked about. And it's called the von Neumann dimension. By the way, so I mean, I did the three regular tree. I could also have done the fourth regular tree, which is E gamma, for gamma being the free group F2. So that was another example. I think I missed it in the list of examples of classifying spaces. So on the tree is certainly contractible, and you have a free action of the free group. And therefore, the fact that we've proven the non-vanishing of H1 for this tree gives us in the end that the first L2 Betti number of a non-abelian free group is non-zero. And of course, this is in line with this theorem of Lackenby that I used as a motivation somehow. The free group itself is certainly large. And it's also residually and finally precise. All right. Dimension. Okay, so first some preparation. So if you want to define, say you have a finite dimensional space, we certainly know what the vector space dimension is, but somehow let's do it a bit differently. So okay, for various reasons I want to work with the complex numbers. For some stupid reason I started with real Hilbert spaces, but we'll switch to complex Hilbert spaces. So let's look at a finite dimensional Hilbert space, C to the n, and let's take a subspace. Then we all know what the dimension is, but I want to stress that the dimension, the vector space dimension of W can be written as the trace, just like that, the trace of the projection of V viewed as an operator. Okay, so the projection onto the subspace gives you a linear map from C to the n, so C to the n, and as a matrix it has a trace, and the trace is just the dimension of W. Okay, so this is an obvious thing, but just by the right choice, I mean, you can compute the trace in every basis, and you just pick the basis. So this, so such a projection is given by the matrix 1, 1, 1, and then 0. Okay, but this is a useful observation, as trivial as it is, because in this Hilbert space setting that we are dealing with, we don't have a priori a dimension, but we will have a trace. And therefore, we will do something similar like that. Okay. Okay. Definition. So there is associated to a group. I will look at the space of bounded equivariant, gamma equivariant operators. L2 gamma to L2 gamma. So this is a subset of the bounded operators of this Hilbert space, denoted by B, L2 gamma. But I want them to be gamma equivariant with the obvious left group actions on L2 gamma on the regular representation. And this I mean, for now this is just a set, but it's actually an algebra. Algebra with involution. It's a very famous so-called Neumann algebra, named the group for Neumann algebra. Such a thing. And now somehow I switched from finite dimensional to infinite dimensional. A finite dimensional for Neumann algebra. So I didn't define what in general for Neumann algebra is, but just say a good example of finite dimensional for Neumann algebra is the algebra of n cross n matrices on a finite on Cn. Okay, and somehow, like we have the trace for these matrices, I want to define now a trace for L gamma, but this is now operator on something potentially not finite dimensional, but still we have a trace, and the trace will be a function from L to L gamma to C, and it's defined by taking an operator, applying it to the unit element of the group that is certainly a vector in L2 gamma. It's one of the basis vectors, it is preferred Hilbert basis. Again, this is an element in L2 gamma, and I take its scalar product with 1 gamma. And this gives me a complex number. And it's called a trace because you have the trace property that you have to check. It's not very hard. That trace property means that if you trace of ST is the same as the trace of TS if you have two such things in L gamma.
So here, by 1 gamma you mean the delta function at 1 gamma?
Say again?
By 1 gamma here you mean the delta function at 1 gamma?
Yes, right. I think of gamma being a subset of L2 gamma, but somehow it's a subset by the Okay, so maybe let's look at an example. So, example. Why is it somehow a generalization of the usual trace? Okay, so if gamma is finite, then L gamma is nothing else than the group ring C gamma. So it's a finite dimensional thing. And now, I wanted to say that L2 gamma is the same. L2 gamma is the same. Actually, L gamma is also the same, but in a different way. L2 gamma is C gamma. And now we look at gamma invariant linear maps on C gamma. Okay. So now, if you look at this definition here, of such a matrix now, since everything is equivariant, this is the same as 1 over the group elements of the sum over all gammas in my finite group. Well, first of all, the scalar product is equivariant under gamma, so I can put gamma here. But then I can put the gamma inside because T is equivariant. So in the end, what we have is this. Okay. And now, if we have now we see somehow that we get, this is just like the normalized usual trace in this situation. But of course, if gamma is infinite, we don't have the usual trace. So we have to do it in this way. But this is how you should think about it. In the finite group case, it boils down to the usual trace normalized by the group order. So now we work with this and define the dimension accordingly. So definition so for a closed gamma invariant subspace, in finite sum of copies of L2 gamma. And this is the level of generality I will deal in this lecture. I mean, you can do it much more general, but this is somehow what I want to do here. For such a closed subspace, we define this von Neumann dimension as this trace that I defined over there of the projection onto W. Okay. Now, first of all, this projection is a gamma equivariant operator. Now you might object. Okay, I did define what it is if m is 1, I did not define what it is if m is not 1, but okay, this is just,
So what's the meaning of it? Is it L2 of gamma to the m or L2 of gamma to the n? And it's W.
yeah. And then,
W.
sorry?
W. It's right inside. Project onto W. Oh, well, okay.
No, but I want to, but I want to view it as an element in this, as a method. I mean, the image will be W.
This is the
Yes.
same as.
So the result depends on m. Somehow, but the left side you should maybe put m.
The m is this m here. So W lives inside L2 gamma n. Okay, so now I did not define what this is, but this is easy because, I mean, such a guy I can view as an m cross m matrix of operators L2 gamma to L2 gamma. Okay, just looking, where does the ith copy go to the jth copy of L2 gamma? So it gives me a matrix of gamma equivalent operators. So in a sense, I can view this thing here as an m cross m matrix with elements in L gamma, and then I just take the usual trace. So I take the traces on the diagonal in the sense I defined it, and it's just sum it. Okay. So so this is somehow the sum I to n of in that sense. And okay, now there are various things to check. You might say, okay, but I can take W and embed it in a, I mean, somehow the way I defined it, it depends on the embedding that I chose. Okay, now there are things to check. Actually, it does not depend. If I embed it further into something different, gives you the same number. And okay, so these are a bunch of not all completely trivial lemmas to check.
By L gamma 3, you mean L2 gamma, or really?
No, here I mean L gamma, because somehow this is an operator. From L2 gamma to the n to L2 gamma to the n.
Definition of
I can view this as a matrix of operators.
Ah, sorry, yes, okay.
And then, okay, so this is L gamma. So this is a definition of a, okay, so this is some number. And now the definition of L2 Betti number is very easy.
So maybe just before you raise this definition of L gamma, maybe for those who see it for the first time, L gamma is, you have L2 gamma is a regular representation of gamma, and gamma actually say by left action, and there are operators commuting with that. For example, the right gamma action, and L gamma is everything which commutes with the left regular gamma action. So it's some sort of a closure of the right gamma action.
Can you give some examples with fractional?
I can give you, okay, let me give you another example. So I gave you one example. I gave you the example where gamma is a finite group, which is a finite dimensional example. Still, it's an important example. But let me give you the example where gamma is the integers.
But when gamma is a finite group, the dimension will always be integer.
No.
No,
Never.
no, almost never. Because if gamma is a finite group, then the dimension of W will be the usual vector space dimension divided by the group order. So as I said, the trace is the usual trace normalized, and it for the dimension it gives you, it's the vector space dimension divided by the group order. So it's a rational.
There is a funny, I mean, maybe you're going to mention this later, but there is a funny fact, right, that this dimension can only, I mean, it takes on some funny discrete set of values.
Yeah, I come to this conjectures, yeah. But to somehow, now it's maybe a good time to mention, so if L2 Betti numbers of finite groups are just Betti numbers of these groups divided by the order of the group, this will turn out. So somehow, in all finite situations, we will not get anything new. it's really the infinite group case that's interesting to us. So now I still have to define the L2 Betti numbers, but somehow I feel I should give one more example of this thing with the dimension and the trace. And this example is the integers. So if you look at the integers, then you all know that this Hilbert space can also be described as L2 function on S1 by Fourier transformation, Fourier isomorphism. And if you look at the equivariant maps on this, which is by definition the von Neumann algebra, and somehow you intertwine it with that isomorphism, you will get L infinity S1, where I think of L infinity S1 as operators on L2 S1 by multiplication operators. Okay, so somehow taking this, intertwining it with this isomorphism will give you in the end a certain set of operators on L2 S1, and it will be exactly the multiplication operators. So it will be the algebra L infinity S1. And okay, I mean, so maybe you have to check it, you write down it slowly. Let's maybe not do it now, just want to mention this, but you can do this very easily. And then the question is, what is the trace? So you have here this trace that I defined. And now you can guess, if I take this isomorphism, what it will be. It will be just the integral. So the integral of f with respect to the probability half measure on S1.
What is the action of Z on L2 S1?
Shift.
No, on the right side.
Induced action.
Rotation.
Rotation.
Sorry, yeah, rotation.
What?
No.
Multiplication.
Multiplication by e to the I,
Yes,
to
sorry.
the right degree.
Yes.
To the right,
Yes,
right
sorry. And I wanted to say one more thing. Right. I wanted to say also what is this? So what is a good example of such a W in this setting? Well, for example, you could take this set, you take all functions on S1 in here, such that f restricted to a measurable subset is constant 0. So this is an example of such a W in L2 S1. And then the dimension, this von Neumann dimension of this W in this picture, just be the measure of A. In particular, you see, you can realize any real number here between 0 and 1 as the dimension. And as you alluded to, there are certain conjectures about L2 Betti numbers that give you some integrality or rationality statements. But this just says that the operators that we consider in the definition of L2 Betti numbers are of a very special algebraic kind. And they are namely the Laplace operators we look at. So now finally the definition of L2 Betti number can be given. So how much time do I have? One minute. Oh, 1 minute is. I do it in
Very long minute.
one Israeli minute. Okay. So, as I said, I'm looking now at a compact CW complex. want to define the L2 Betti number of x. So I have this x tilde, and this x tilde I have an action of my fundamental group. This is my deck transformation, this is the setting I'm looking at. And let's look now again at this L2 cohomology groups. In the L2 cohomology group of this so there was this complex, as you remember. And so on and so forth, but what is it? So these are L2 functions on the set of n cells of x tilde. But what are the n cells of x tilde? Well, down in x, we have, since we have a complex CW complex, we have a finite number of n cells. Okay? And in x tilde, we have above each n cell of x, we have a whole gamma orbit of n cells. So somehow, if we look at the L2 functions on these n cells in a very natural way, and the isomorphism is given by the CW structure, this is sum of L2 gammas, and the sum is here over the set of n cells in X. Again, I have, for each n cell in X, I have a whole gamma orbit of n cells in X tilde, and then I take the L2 functions on it. I can write it as the sum over the n cells in X of L2 gamma. And this is an isomorphism S gamma modulus.
And of course, the sum is the L2 closure.
I assume complex, so it's a finite sum. And there are various issues if it's not complex, so I don't want to deal with it now. So now the Laplace operator that we defined here is the guy acting on here. And it's actually, everything is equivariant, everything commutes with deck transformation. So this is a bounded equivariant operator on this thing. In particular, the kernel of the Laplace operator that we said is the same as this reduced thing is a subspace of this guy and therefore I can now do the definition that the L2 Betti number of x I define as this gamma dimension, gamma being the fundamental group of x of this space. Okay. So this is the number, and now, as Nick said, there are these conjectures. One conjecture, for example, is that if the fundamental group is torsion free, this is always an integer. And as you see from this example with L infinity S1 and L2 S1, it's far from clear a priori that you get an integer number here, because this can take any real values, but somehow these things, they come from a discrete combinatorial geometric situation, and so far we don't have a counterexample to the conjecture that this is an integer if the fundamental group is torsion free. And in the last lecture tomorrow I will prove this fact if the fundamental group is a free Abelian group. Sorry, is a free non-Abelian group. So this conjecture is the Altier conjecture, and I will deal with this in the third lecture. Somehow prove it for F2. Okay, so let's finish today.